let me begin my talk. If you have been closely following jet physics, this talk may not be very useful. I mean, you may not get something new from this talk, but this talk is intended to be useful for someone who is not familiar with jet physics or who just came to the field. I mean, someone who is not obviously familiar with the entire heavy ion physics. So I just want to give a help to those people. And after this talk, I hope that if you happen to see a jet talk in a conference or workshop, you may at least get the context before the talk, even before the talk, and at least understand quite a few part of that talk. That's my goal from this talk. So I'll start with the introduction and saying a few words about jet definition in QCD matter and what measurements are there in experimental jet physics and how to deal with the background in jet measurement. That's going to be my introduction. And I'll show some recent jet measurements at RHIC. So I marked as at RHIC, but that corresponds to at in STAR, because STAR is more or less the only collaboration that has the jet measurements at RHIC. And I'll show more results, more jet results, which is the STAR's contribution at Quark Matter 2022. Okay, let me start. So jets, when you think of a jet in heavy ion collision or in PP collisions, you may think they are from hard scattered particles. That's something very basic. So jets in vacuum, in PP, such as in PP collisions, the hard scattered parton fragments into final state particle like this. And then once we algorithmically recombine those final state particles, that becomes a jet. And jets in vacuum are very well understood in perturbative QCD framework. So the perturbative QCD calculation explains or describes very well with the experimental data. And once you have this hard scattered partons in heavy ion collision, that's jets in QCD matter. So hard scattered partons are produced at the very early stages of the collision. So it experiences every evolution of the medium and it interacts with the QGP as they traverse it. And that's why it is very useful because we know the baseline and it interacts with the medium. So we can think of the medium property via the jets. And any modification to jet observables are due to the interaction with the QCD medium. And that's what we call jet quenching. And one of the benefits of the jet measurements it has a very broad kinematic reach. We can probe the medium over a wide range in scale from low PT to high PT. So it's very similar to bullet in air and bullet in water. So this bullet is our jet, and air and water can be like a vacuum and this QCD medium or quark-gluon plasma. So when you compare the trajectory of bullet in the air and trajectory of bullet in water, of course in water the trajectory in water is different from those in the air, and that somehow tells something about the property of this water, and also if you compare like a viscosity of the water, and also if you compare the temperature changes in the water as the bullet traverses it, it says something about specific heat of water. So it gives a lot of information about the water if you compare the bullet in air and bullet in water. So it's very similar. We know the vacuum baseline, and then once we see the what's changing in the heavy ion in the quark-gluon plasma, we can think of the property of quark-gluon plasma. So this jet measurement has started at the very early days of the RHIC running. So RHIC began to run, or RHIC began to operate since 2000. And the first generation jet measurements at RHIC was via high momentum hadrons. So I said jet is an algorithmic recombination of final state particle, but at the very beginning, we only looked at high PT or high momentum hadrons. So let's consider like a 20 GeV hard scattered parton. The parton is 20 GeV and it may produce like a 15 GeV particle, or sometimes it just produces a whole bunch of low PT particle. But whenever we have a high PT particle, that high PT particle definitely comes from hard scattered parton. So that's why we only consider high momentum hadron. It's a proxy of a hard scattered parton. So this is the paper from 2003 from STAR. So high PT particles are a proxy of hard scattered parton. And in this paper, they compare the number of high PT particles produced in heavy ion collisions compared to that in PP collision. And in terms of the RAA, which is the ratio between those produced in heavy ion collision compared to those produced in PP collision. So high PT charged particle yields are suppressed in central heavy ion collision, which is 0 to 5%. And it's not much suppressed in 60 to 80% collisions. And also another paper that I want to mention is the same year paper, PRL paper from STAR. So now we have a high PT particle here, and we investigate the two particle angular correlation with the associated particle with the lower PT. And this is called a money plot. So if you compare PP and heavy ion and central heavy ion collision, we do have a suppression of the recall region or back-to-back correlation in central heavy ion collision. So suppression of both high PT particle yields and back-to-back correlations became the evidence of the QGP. So this high PT particle measurement or some proxy object measurement became the evidence of the quark-gluon plasma. So at the beginning of the RHIC running, we wanted to check whether we could really see a quark-gluon plasma or not, but this result really confirmed that we could see the quark-gluon plasma in heavy ion collisions at RHIC. And after a decade, we now have a next stage. So at the beginning, we used the high PT particle, but now we really use jets. So it's a recombination of final state particles. So jet reconstruction algorithm, we use jet reconstruction algorithm, and that satisfies infrared and collinear safety, such as anti-KT algorithm. And it is, of course, a better proxy of hard scattered partons. So it is a hard scattered, high PT particle are just a part of the entire parton momentum. But now if you use jets, it's more closer to the parton momentum. So it's a better proxy. So what questions are we trying to answer by investigating jets in heavy ion collision? There are many questions that you can think of, such as how does QGP respond to the external out of equilibrium probe, such as jets, or how can we use jets to probe the microstructure of the QGP? What is the resolution scale of the medium? How can we measure that? What can we learn from the mass dependence of jet quenching, and many others? There are many questions that you can think of. And also there are many jet observables, and each jet observable is connected to one or multiple questions in the above. So we can probe different aspects of jet quenching with the many jet observable. But in the end, we measure the same physics, the jet quenching physics, in multiple ways. So the important keyword is consistency. So by measuring different observable associated with jets, but are we seeing the consistent picture of jet quenching or not? That's the keyword. So what have we found so far? So for the last 20 years, what we have found can be sorted out in 3 different categories. So as jet traverses the medium, it loses energy. By looking at this gluon Bergström length, it loses energy. And also jet substructure is modified as it traverses the medium. And also the jet angle is deflected, so jet deflection. So these 3 things are the main findings that we have found. And I want to show a chart. So this is a friendly junior day. So I want to show something that I prepared specifically for this. So I spent quite some time to make this chart. So this is the basically summary of all jet measurements in modern heavy ion collision. It's from CMS, Atlas, ALICE, which are LHC experiments, also STAR and Phoenix. And of course, I dropped some PP collision results, which is from high energy community, but I included more or less the heavy ion communities jet measurement publication. And two caveats, preliminary results are not included, and results with jet reconstruction only, they are included here. And once the rows are from different collaborations, the columns are different observable. So if you are from different fields of the heavy ion physics, like if you are from a heavy flavor group, you can make a similar chart. So different collaborations and maybe different observable like a D meson or J psi or J psi V2 or whatever. You can make the columns. I mean, once you have this map, it's like a puzzle. Oh, there are some missing puzzles. So you can tackle on this puzzle and you can fill out the entire puzzle to have an entire picture. So that's a good homework that you can try when you begin a certain analysis. So in order to find where your analysis fit in to the whole picture. Well, I started to making this chart when I began my jet analysis, when I started my postdoc. And I've been updating this chart for a while. Anyway, what I wanted to say is the three top columns, which are from LHC, has many publications compared to the last two rows, which are from Star and Phoenix. So there are many publications from LHC and a relatively small number of publications from RHIC. And RHIC started in 2000, but LHC began to take data from 2010. So RHIC has much longer history, but why do we have a small number of publications compared to the LHC? That was my mystery at the beginning, but I do have the answers now. Well, maybe other people have the answers as well, but this is my answer. So let's consider jet measurement at 200 GeV. So this plot is showing cross-section of jets at 5 TeV and 200 GeV. So 5 TeV is red and 200 GeV is black. And you can see that the cross-section at 200 GeV is much steeper than the 5 TeV. So if you want to measure jets, our jet PT ranges are, let's say, between 20 to 50. We can have a sizable number of jets at 200 GeV. But at the 5 TeV, we have much more jets at high PT. So when we think of the jets at the LHC, the lowest PT starts from almost 100 GeV. But at RHIC, we can't measure anything at 100 GeV. So their jet PT ranges start from 100 GeV up to 1 TeV. But at RHIC, the jet PT ranges are from, let's say, 15 to 50 GeV, so much smaller, much lower PT ranges. And once we have to restrict ourselves into low PT ranges, we have to seriously consider about the fluctuating background. Because fluctuating background, it has a level of 10 to 20 GeV. So let's say we have a 15 GeV jet. That 15 GeV jet can be from a hard scattered partons, which is really a jet, but also just combining some background particle, which has nothing to do with the hard scattered parton, they can still make a jet, a 15 GeV jet, which is what we call combinatorial jet. So a lot of parts are from just background, not from a hard scattered parton. So we need a certain technique to distinguish those two. So we had to devise the technique to deal with those, and that's why I think we have much less number of publication at RHIC compared to the LHC. At the LHC, we didn't really have to worry about it because let's say now we're looking at 500 GeV jet, and everything is really from hard scattering. Nothing is from background. But at RHIC, our range is much smaller. The PT is much smaller. We really have to consider this combinatorial contribution more seriously. Anyway, the LHC developed large number of techniques, not only this background, how to deal with background, but they also develop many different things. So now RHIC has a certain method to deal with it, and I'll introduce those. So how to resolve this combinatorial jet issue. So as I said, challenges in jet measurement in heavy ion collision is large fluctuating background. There are two main ways that we deal with this. The first is using semi-inclusive approach, which was used in this paper in 2017. And the other is requiring high momentum constituent, which was used in this paper as well. I mean, 2017, different paper. I mean, we have two different paper using totally different methods. So first, with the semi-inclusive approach, we look at high PT particle first. So as I said, high PT particle is definitely from hard scattered parton. So we know now, once we have a high PT particle, we know that, oh, there's a corresponding high PT parton. And in the opposite direction, or the recoil direction, there should be back-to-back hard scattered parton as well. So we're now looking at the recoil region of this hard scattered parton, I mean, high PT particle. And we're looking at jets in the recoil region. And we have a way how to deal with combinatorial jets in this range. So that's what we call semi-inclusive approach. And second is requiring high momentum constituent. So as I said, once you have a high PT particle, that means there is a hard scattered parton here. So we first find hard scattered high PT particle, and then reconstruct a jet around it. And that means this jet corresponds to this hard scattered parton. So that's what is used in this paper. And that's the second method that we do, I mean, that we have. So now I want to show some recent jet measurements at RHIC. So in previous slide, I show two methods, one semi-inclusive approach, the other with requiring high momentum constituent. So all the recent jet measurement at RHIC uses one of these two. All the result at the heavy ion collision use one of these two methods. And I'll mark it, and I'll mention that what method is used in that in a specific analysis. So I'll first start with the inclusive jet yield. So this is the part of my personal chart. So it's the first category, inclusive spectra, which is the most basic measurement. So inclusive charge jet yield, a publication was online in 2020 in PRC. It basically showed the spectra at the different R and 0 to 10% and 60 to 80%. So it's a central collision and peripheral collisions. And one funny fact is that the initial preliminary results were shown at Quackmatter 2009. It has been 11 years from the preliminary results to the actual publication.
Can I have a question? Sorry.
Go on. Yes.
You are saying that at different R, what does it mean?
Okay. That's something that I didn't really define it. So once we reconstruct a jet, we can make a big circle and combine all particles within the circle. That's a large R. Like R is a square root delta phi square plus delta eta square. So we can make a large radius and combine all particles within that radius. And we can also small radius and combine all particles within the small radius. That's what we call jet radius. I mean, it's not exactly it, but it's similar to those concepts. Like a large R means we are combining large radius and combining many particles around it. A small radius is a small radius. So that's what I meant. Did it make sense?
Yes, thanks.
Thank you. Yeah. So the initial result at 2009, but the final publication in 2020. It has been many people's efforts in this paper, and I'm very happy to see this paper 2 years ago. Now it's 2 years ago. Anyway, this was in 2020, but at the LHC, Atlas, CMS, ALICE, they published paper in 2015, 2017, 2015. But this was the first RAA papers from each collaboration, but they have more. So they began to operate in 2010, but they have their first RAA papers in after 5 years or 7 years or 5 years. But they now have more. So once they have these RAA papers, they set a certain strategy or correction ways. So they make more papers. So they have papers at different energy or different collision systems. So there are more RAA papers, but they do have them. But we also have them now. Have one now, the charge state RAA. So RAA is the ratio of jet yield in heavy ion collision with respect to scaled PP collisions. So this is the RAA Pythia, so the relative to the Pythia events. So inclusive charged particle jet spectra at 200 GeV with respect to the Pythia. And this paper shows the theoretical calculations here as well, but they are all kind of consistent with the measurement. So greater precision is needed. And perhaps, I mean, I hope that with the run in 2023 to 2025, we have a better precision, so we can make some comments on which calculation is better than the other. That's what I personally hope. And in this inclusive jet yield, we require a high PT momentum constituent. So this is the jet, but we require a high PT particle. But when we require a high PT particle, we may bias our jet selection, because even though the same PT jet, some jet has a high PT particle, but some jet may not have high PT particle. But if we require high PT momentum constituent in our measurement, we are biasing our jets into a certain fragmentation pattern. I mean, all the jets we have has the high PT particle, and that is not an inclusive jet. So we had a strategy how to deal with it. So we set the unbiased region. So if the jet PT is less than, in this case, like a 14 GeV, they are more or less strongly biased. But after a certain lower cut, this jet population is not really biased because of this requirement. So we estimate where the bias started or bias stops, and we just report where we have this unbiased region. So that's this strategy. And not only jet RAA, we also showed jet RCP, so comparison between central and peripheral collisions, so the ratio between central and peripheral. And so and this is RHIC 0.2 and this is RHIC 0.3, and blue is from star, red is from ALICE. So the ALICE has a larger PT range, and these closed markers are from jet, and open markers are from a high PT particle, the single particle. So different spectral shapes between ALICE and star, but similar magnitude of suppression is observed at RHIC and LHC. So their level of the RCP is very similar. And also the magnitude of suppression is comparable to that of charged hadron. So the charged hadron has this shape, and the level of suppression is also very similar. That's what we learned from this paper. And the second result that I wanted to show is semi-inclusive jet yield. So in my personal chart, it's on the second category. So once you have a high PT particle, we investigate the jet yields in the recall region. And we call it ICP, which is similar to RCP, but it's within the semi-inclusive measurement. So similar level of suppression via ICP to charged particle jet RCP. So the level of suppression is similar to the previous slide, and it's definitely a semi-inclusive approach. And this is using just all high PT charged particle as a trigger, but now we have more results, the upcoming quark matter and publication. So semi-inclusive jet spectra with identified trigger particle. So charged particle jets in the recall region of direct photon and pi0 trigger. So in this picture and in this publication, we used high PT particles, but now we can use high PT pi0 and high PT direct photon. So different trigger particles may represent different in-medium path lengths or color factor and parton energy. And this is a preliminary result. We have updated results as well, but I'm just showing the preliminary results here. So similar level of suppression between direct photon and pi0 triggers were observed at RHIC 0.2 within uncertainty, but there are more results, and it's coming up very soon. And so just wanted to show that there are efforts or ongoing analysis in this aspect. And the third analysis or third result that I want to show is AJ, the diet imbalance, which is in my third category. So it's AJ is defined here. So jet is always back to back. So leading jet PT minus the recall region subleading jet PT over the sum of two momentum. So if they are the same, AJ should be 0. And if the moment PT of these two back-to-back jets are different, AJ has a certain value larger than 0. So this is the results. So this is the black dots are from PP embedded into heavy ion environment, and red is from heavy ion. And they do show a different result with RHIC 0.4. And in this measurement, we require a high PT momentum constituent to identify jets from the hard scattering. For RHIC 0.4 jets with higher PT constituent, more dijet momentum imbalance compared to PP is observed. So it's a bit complicated picture. So we can reconstruct jets only with the high PT constituent, and if we do that, they are very imbalanced. But I mean, when I say imbalanced, PP and AA are different. And that means jet quenching effects are there. But once we include soft particle like a lower PT particle, then balance is recovered. So PP and heavy ion, meaning AA, are more or less similar. And when we use the smaller radius jets, this balance is no longer recovered. So PP and AA are different. So this tells the softening of jet constituent and broadening of the jet structure. So it gives a certain message from this measurement. And the next is the jet fragmentation function and jet shape. So two jet structure measurement. So jet fragmentation function is so this is a jet and this is a constituent. And Z is the jet fragmentation functions observable. The Z is defined as this. Once you have a track or constituent, we project into the jet direction and measure this PT in the longitudinal momentum direction. And that is over jet PT. So distribution of longitudinal momentum fraction of particle with respect to jet, that's the jet fragmentation function measurement. So 1 over njet and dn dz. And jet shape is once we make a ring and then we measure the energy within this ring as a function of R. So distribution of jet energy is a function of distance from the jet axis. That's what we call jet shape measurement. And the jet fragmentation function measurement in star is using semi-inclusive approach, and jet shape measurement is using this requiring high momentum constituent technique. So these are the preliminary results. So jet fragmentation function at 40 to 60% centrality, and this is a jet shape at the 0 to 10% centrality. They are still preliminary, so more results are coming up. And the last results that I wanted to share is one of the jet substructure measurement at RHIC. So you can see 3 papers, and in particular, all the 3 papers are kind of recent. Within slightly over 1 year, we had 3 publications. I want to shout out to Raghav because he contributed to a large portion of his effort into these 3 papers. So the only paper that I want to show is the third one, the opening angle 0.2. That's what I personally marked it because that's in heavy ion collision. Other 2 are from PP collision. So in this picture, this is a picture that I showed earlier. I just showed the 2 back-to-back parton, hard scattered parton, and I made a circle just to specify that we are reconstruct jets around this hard scattered parton. And the parton fragmentation is not really shown in this picture. So I just made a 1 line, just a hard scattered parton, but in fact, this parton also evolves even before it hadronizes. So hard scattered parton fragment into another parton or gluon, and then until it hadronizes. So depending on how it fragments, it may have different structure. So sometimes this parton can fragment into partons that are far from each other, but sometimes it can fragment into two partons that are close to each other. So depending on how the parton fragment, this substructure becomes very different. So the question is jet quenching dependent? Is jet quenching very different depending on the opening angle of this jet? That's the question. And this question is related to coherent length of the medium. If the coherence length of the medium is small and it can distinguish these two, then the jet quenching level of jet quenching should be very different. But if the coherence length is larger than this scale, then the medium cannot distinguish these two jets. So everything is related to this question. And we measure, it's accepted in PRC, but I don't have a number now. But the thing that we did is once you have a jet, like R equal 0.4 jet, we have the constituent, jet constituent, and we reconstruct subjets. Subjets are from the smaller radius jets within the main jet, within the original jet. So once you have the two highest PT subjects, we investigate the distance between these two subjects. So if the distance between these two subjects are large, that means this delta R is large, so we have a wider jet. And if the radius distance between these two subjects are small, that means narrower jet. So the jet substructure is a bit narrower than the other. So we categorize jets based on this distance between two subjects. So theta Sj is the distance between two subjects. So we have two different category, and this is more or less inclusive category. And we measure the AJ, the dijet imbalance for different category jets. And we found low dependence. So energy loss from it's equivalent to the energy loss from a single color charge as it traverses the medium. And it can be interpreted as larger resolution or coherent length of the QCD medium compared to the scale of this jet substructure. So that's the physics message that we have found. So that's the they are the most recent results from STAR at RHIC. The jet results highlights, and more jet results are coming, and particularly for the Quark Matter 2022. So there are 3 talks that JetCo members are presenting at the Quark Matter. Of course, there are more posters, but I just want to mention 3 talks that we are presenting. So first is the inclusive spectra part. So system size dependence of particle production and collectivity from the STAR experiment at RHIC. So this talk is combining multiple small talks, including things from CF, and is it FCD or CF? Okay. And also from our own members. Okay, FCV, okay, thanks. And so it shows the high PT particle RAA in isobar system in comparison with smaller and larger collision systems. So this is the main part that we are showing, but along with the PA and gold-gold collision. It's a smaller system, and how RAA changes or in compared to these two systems. That's the one thing that we are showing. And the next is the measurement of medium induced modification of jet yield and equiplanarity using semi-inclusive direct photon jet and pi-zero jet distribution in PP and heavy ion collision. So it's the extension of what I mentioned earlier. So we had preliminary results, and we hoped to have this result published before the Quark Matter, but maybe not. Then we can show the preliminary results. So we have a direct photon and pi-zero as a trigger particle, and we can investigate jets in the recall region, and we can measure the yield, the semi-inclusive spectra, and we can also the equiplanarity, which is the angle between this trigger and the jet, how the jets are deflected relative to the trigger particle. So I mark it as a within the ETC, but it will be presented at Quark Matter. The third is a heavy flavor text jet. We had nothing before. It's called an investigation of Quark jet spectra and shape modification in gold-gold collisions. So the heavy flavor tag jet can be many things. So some strategy really measure the C jet or B jet, but some jet measurement uses like a J psi jet or D0 jet. And in this analysis, we use D0 measurement jet. So once you have a D0, we made a circle or the radius and reconstruct jets. So we're looking at the jets containing a D0 measurement, and then we investigate the spectra with the yield and also jet shape, with jet shape of this jet containing D0 measurement. That's what we are going to show at Quark Matter. And there are more ongoing analysis in star JetCo PWG. So I just counted our ongoing analysis and try to fit in my own chart. And we are filling up almost everything except this one. There can be, but we definitely have a certain analysis, more than one analysis in each category. And the JetCo PWG members are working on various topics in experimental jet physics. So we are a very active group. And I prepared one slide for someone who is thinking of beginning a jet analysis. So for jet analysis beginners, so I want to comment on beginning a jet-related measurement in STAR. So you can entirely start a new jet analysis, or you can combine your own analysis to some jet measurement. Like if you have measured J psi before, then you can combine your J psi with the jet, that becomes a J psi jet, like a Chen does. Or if you are familiar with a certain other observable and you want to have a certain way to combine with the jet measurement, you're of course welcome to do that. But beginning a jet-related measurement in STAR, maybe you may think it's kind of difficult because you are not familiar with that. I wanted to comment on it. So when you start a jet analysis, what I wanted to say is, I think you should make a plan in advance. In particular, you have to make a whole plan for your analysis strategies, because at the later stage, I mean, once you spend quite some time and after like 6 months, you realize that, oh, I should have done this. That's not really a good thing. So when you first start a analysis, you should think how to deal with combinatorial jets. As I said, there are two established strategies that we deal with combinatorial jets. So what strategy is more appropriate for the observable? So it depends on the observable. So you can think of what is more appropriate for your observable. So that you have to think of it in advance, and you should make a plan in advance. And also, which data set and triggers are appropriate for the observable. So in jet analysis, we require high PT sector. So mean bias data may not be really a proper data set. So you may need like a high tower trigger or some L2 gamma trigger. That's what we've been using. So you can think of them as well. So if you are not familiar, you can ask me or Raghav or other JetCo members as well. So you have to think this in advance as well. Also, jet, we are using certain jet reconstruction framework. So it may not be easy to get in, or it may not easy to develop from the scratch. And there's a coding guide. So I want to shout out to Joel for making this. So Joel's Star Jet Framework GitHub is available. So Joel is working on jet shape in Run 14 Run 14 gold data set, and he shared his code in this GitHub directory. So you can take a look at it. It's very well commented, and it's nicely dealing with the PicoDST files. So you can get some idea on how others are dealing with the jets in reality. So it gives it uses the fastjet package, so you can start from his code. I mean, that's something that I can recommend. And also, you can come to our weekly meeting, which is the 9 a.m. on every Thursday, and you can get more comments. I mean, there are more experts in our group than myself, so you can get very helpful helpful advices and recommendations if you start a new analysis, with the JET. So that's my last comment, and this is my summary. JET measurements in relativistic heavy ion physics program investigates the property of quark-gluon plasma, and JET provides a unique tool to study hot, dense QCD medium. And in particular, JET in vacuum and medium, they are theoretically well controlled in many aspects, and it has a very broad kinematic reach and improve the medium over a wide range in scale. And JET has a complex structure, so many complementary observables that prove similar physics, and they require consistent picture. And in particular, and JET measurements at its star, so various experimental data are available and more to come, and theoretical efforts to describe data are needed, and better precision will be achieved with upcoming runs in 2023 and 2025. And that's it. Thank you.
So thank you once again for the talk, and there's time for questions.
Yes. Hi, Hansel. Very nice talk,
Hey,
and I really appreciate that trust that I want to utilize in my own analysis. I have a question on page 14. Could you explain a bit more about the resolution scale for the median? You mean the QTB, right?
So when I explained this, I mentioned about the resolution scale here. Let's start with the more basic physics concept. So let's say you have two different points, and each point emits a light. So two light sources. And when you get closer to the two light sources, you can distinguish these two, right? But when you get far from the two light sources, and as you go further and further, there is a certain point that you cannot distinguish these two. That means your resolution is not good enough to distinguish these two, right? And if your telescope or if your eye is better, then this distance becomes even larger, right? So there is a specific resolution scale that something can have. And our QGP has the similar concept. So let's say its resolution scale is small enough to distinguish these two, then the measurement result between these two should be different, or maybe the same, but at least we can distinguish something. But if the resolution scale is large and we cannot distinguish these two, then they should be really the same. So that's why I said it is related to the resolution scale of the QGP medium, because QGP medium can, depending on the resolution scale, it can distinguish these two, or it may not distinguish these two.
Okay, thank you. Now I understand this part, and
Okay.
I have a broader question on the same page, the page 14.
Okay.
Those questions you raised are very nice. What's the progress status of the whole JET community, including STAR, answering those questions?
That's a very nice question, and I seriously hope to have a better answer than what I have now. But so it's my personal opinion. So different people may have different opinions as well. But I personally think we do have some answers. But in order to have answers, we need a collaborative efforts between experimental community and theoretical community. And one problem that our JET community is facing is how to make a consistent picture between theory and experiment. Because let's say an experiment reported something. So let's say a JET experiment report a certain result, and then some theories try to feed the data to their calculation, and they say, oh, this is what, and this is A, this is B. So it's always like a ping pong between experiment and theory. But the problem is we do not have a very well resonating picture between experiment and theory. So we are trying to answer this, but it's not really concrete, I would say, at this point, because of the inconsistent baseline between experiment and theory calculations. So there are ongoing efforts such as JETScape, but it's not at the level that we are like, we can now move on because we have every answer. That's not the stage as of now, but we are trying to approach to that direction, I think. And that's my opinion. I mean, we are trying to do it, but not at the level that we are totally satisfied with these questions and answers. That's my personal opinion. Though, of course, different people have different ideas.
That's great that there are still more questions for people to work on. Thank you for your answers. Thank you.
Thank you.
I think that my opinion is also like this, that this is a general problem, maybe not problem, but issue, let's say, that in most of observables in our physics, we need this agreement with the theory data, so the simulations, and it's quite tricky to get there. And or we are a bit like trying to catch up with theory, or they are. And sometimes I think we are missing this like way of communication. But this is good because there's still some way to improve. And this is up to us juniors, because this is, you know, like future is in our hands. So I see one more question.
So actually I wanted to like follow up a bit on Ding's first question about like the resolution scale. So is it that when you like the jet fragmentation is below the fragmentation, the resolution scale, when that's happening, does it actually mean that like the quenching mechanism is going to be different? Or like, for example, when you raised up this like just light source analogy, yes, we can, differentiate the two light sources when they're like far apart enough, and if not, then we can't, and it's most likely just appears to be like one light source to the like naked eyes. But the luminosity is going to be still the same, and otherwise it's like, the like those quantities are still going to be the same whether or not we can resolve them. Is it like different in the ways of this like jet fragmentation picture?
Tone, so I don't think I fully understood your question, but okay. So when I say these parts, and also not me, but the entire paper. So we do have the paper now, right? So this paper is on archive. In that paper, this statement is based on a theory calculation. So a theory calculation is predicting that if the resolution scale is small and it can distinguish these two, so basically 2-prong and 1-prong, their jet quenching level should be different. That's the prediction from the theory paper. And my statement, or the theory paper statement, is based on that one. It's not just claiming that they should be different out of nothing, but it's based on there's a theory calculation.
Okay, yeah, I guess it's like that theory part I didn't like 100% understand when I was reading the paper. So yeah, okay, I'll try to go around. Thanks.
Yeah, thank you.
There's not a question, just a comment. So Hansel, on your table, you had this one box that was at the end unfilled.
Yeah.
There's Anika and Rosie. Anika defended her thesis, but that was an XJ gamma analysis.
Yeah,
so that is
I wanted to fill that
progress.
as well. Yeah, I was aware of it, and I considered whether I should fill in or not. But you see this caveat here: preliminary results are not included.
No. I mean, at the very end, you had a box saying that this is ongoing. Almost everything. That one was unfilled, so that is ongoing. That's all.
Yeah, thank you.
Yeah.
Yeah. Yeah, I'm just curious. So since you mentioned that one issue of jet analysis is discrepancy between theory and experiment, I'm just curious, I know there are multiple ways to study jet, and will you say that jet analysis is model dependent? Like in your in the jet analysis, do you rely on model to extract some observable?
So in theory calculation, let's say you have a jet in PP, and then once you place this jet in heavy ion, I mean quark-gluon plasma, you can basically have the same jet in the heavy ion in the quark-gluon plasma and calculate its interactions in the calculation. But in experiment, it's not really the same because we have the experimental limit. So like in our method, we use the semi-inclusive or requiring high momentum particle. That is not really accounted in the theory calculation. So there's a discrepancy. And also, for example, we start from the 0.2 GeV particle, right? Like a 0.2 GeV particle is the minimum PT particle that STAR can consider. But most of the theory calculation does not have that limit. It just gives the whatever lower limit has, but we do have the experimental limit. But it's not really accounted in the theory calculation, and those small discrepancies may make a large difference at the end. That's what I meant between the discrepancy between theory and the experiment. And there are ongoing efforts such as JESCAPE. What JESCAPE does is it gives the like a Jiang, but it's combining multiple theory in the multiple stages, like a hadronic stage or hydro stage. It has multiple stages, and they comes to the play in the same framework. So the theoretical calculation can have a corresponding result as the experiment. So that's the part of those efforts. So that's what I meant. Not only like a jet measurement has to depend on a certain theory calculation. It doesn't really mean that.
I see. Thank you.
Yep. Thank you.
It would be great to add what SPHENIX plans to measure on this on your table. And I think the good comment is that first of all, your table is becoming a legend now.
So one thing, it's a very good comment. And one thing that I want to mention is SPHENIX is particularly focusing on the heavy flavor tech jet part. So SPHENIX is working not only on jets, but also it has an excellent heavy flavor tracker. One of their intention is to heavy flavor as well. So heavy flavor jets is one of the main purpose or the main design in their concept. So I expect to see lots of result in this category.
So the thing which is quite interesting for me is that we are comparing here, well, different energies, of course, but generally, so this was probably the aim of this comparison, but we also compare completely different systems. I mean, like gold and lead, this is very different. And as I would expect, in my imagination, is that when we have a bigger, a system collided, and this overlap zone is relatively bigger, so the multiplicity is bigger, so we expect, I don't know, bigger amount of QGP there, the suppression will be bigger. I mean, this is really interesting that you see these two totally different systems overlapping each other.
I entirely agree with you. It may feel strange, and if you feel that this agreement is strange, I think that is absolutely normal, because I thought the same way at the beginning. But I would say, well, the thing that I want to mention first is if you look at the spectra, not the RAA, the shapes are different between ALICE and STAR. STAR's results are much steeper than ALICE. But once we have the RAA, this shape information is just washed out. We can't really see the spectral shape anymore. You just see the ratio between the central and PP, central heavy ion to PP. But so the RAAs becomes very similar, although their shapes are very different. So these are, yeah, I agree that they are strangely similar, and their level is very similar, and that's what we see. I mean, I don't have a solid answer why we are seeing very similar level of suppression. I don't know. I mean, I don't have a solid answer as of now, and the this theory calculation, they are trying to answer the 200 GeV and 5 TeV or 2.76 TeV with the same model. So that's the whole interpretation. I don't have a good answer for that, but yeah, to me, it's also kind of strange as well. It's a coincidence.
Good. In this case, I'm happy that's obvious, and I missed something. Okay, but thank you once again, and I hope see you on the next meeting, like in person. Thank you a lot.